All right, so last time we saw that this reaction is not endothermic, but it is in fact exothermic for sure. And so we have to kind of think about why this discrepancy is occurring. And so if we think about our measurements here, what we're talking about is, taking away an electron, adding electron. We're talking about this stuff being in the gas phase. And we're talking about it being by itself. So when you form kind of this, chloride or this positive sodium, you're talking about it being by itself. But as we saw in the previous video, when we form an ionic compound, we don't have things by themselves. We have our ions surrounded by one another. And this positive negative interaction is very favorable, very lowering in energy. And so there's a lattice where all ions are bonded to the neighbors. And as we can see, that's not the situation. We're talking about ionization and electron affinity. And so this is what's known as the lattice energy. And it's this favorable interaction that makes our reaction so exothermic. And so we can't measure lattice energy directly, but we can use what's known as the Born Haber cycle to figure it out. And so it's a series of hypothetical steps in order to get the lattice energy, and it's an application of Hess's law. So think about the energy chapter and Hess's law. So we have the overall reaction here of some solid sodium interacting with some gaseous chlorine to form some solid sodium chloride. And we can measure an energy of this reaction, right? A delta H of formation. We could put this reaction in a calorimeter and get out the final reading. And just like you saw in the video, it for sure is exothermic. So negative 411 kilojoules per mole of reaction. And so in order to figure out where this energy is coming from, we can break it up into some hypothetical steps, measure the energy of those steps, and then see how much our lattice energy is contributing to these steps. So in the first step, we have solid sodium, and we actually have to turn it into a gas for it to react. Solids are relatively unreactive. And so if you're thinking about going from a solid to a gas, that is an endothermic reaction. It's called sublimation. Sublimation. And so that's definitely endothermic. So that's a positive 108 kilojoules, right? It takes energy to go from solid sodium to gaseous sodium. You notice the next thing we have to do is break apart our chlorine gas. Our chlorine gas comes in Cl2, right? It's a diatomic gas, so we have to break it up into just one Cl. And so if you're breaking stuff apart, you have to put energy into breaking it up. And so this delta H is also positive, in this case, 122 kilojoules. The third step, we've got our sodium as a gas. Now we have to remove that electron. So sodium as a gas, losing its electron. This is also an endothermic reaction, right? We saw that up here in terms of the ionization energy, plus 496 kilojoules. Now that we removed the electron from sodium, we could give it to chlorine. This is definitely exothermic, right? Chlorine has a negative electron affinity, or releases energy when it gets an electron. So this is negative 349 kilojoules. And in this fifth and final step, we have the chloride as a gas combining with the sodium plus as a gas to form our solid sodium chloride. And so this delta H is our delta H of our lattice energy. And so we don't know what this is. We can't measure this directly. But what we do know is that the overall reaction must be a sum of its step. So this delta H of formation must be the sum of all 5 of these steps. Right? And so we can write the delta H of formation is equal to the delta H of step 1 plus the delta H of step 2 plus the delta H of step 3 plus the delta H of step 4 plus the delta H of our lattice energy, or step 5. This is what we were interested in, so I kind of gave it a slightly different name. And then we have all of these other numbers, so we can plug them all in and solve for the delta H of this lattice energy. And you see it's negative 788 kilojoules. And so this lattice energy, you can tell it's very exothermic. And so this is kind of the energy benefit from being in a lattice. Right? Positive and negative charges are attracted to each other. So if you let them be close to each other, that's a positive scenario, a releasing energy scenario. Think about if you have 2 magnets, right? And you try to pull them apart, that takes energy. If you just let it go, they'll come together. And when they come together, what they're doing is releasing energy. So this is just a series of hypothetical steps to solve for this lattice energy. Check out your homework for some examples. You won't always be asked to solve for lattice energy. Sometimes you'll be asked to solve for other stuff. And then here's just kind of a picture of this diagram, right? So first off, we've got to make the solid sodium, right? Second step, split up the chlorine, ionize the gas. All of these are endothermic, so they're taking energy. Give the electron to chlorine, that's exothermic. And then finally, this lattice energy, right? And so all of these things must sum to equal the delta H of formation. And so using that, we can solve for lattice energy or any of the other steps if we did have lattice energy.